So today we're going to work on curve sketching still, but we're going to focus in on some trig problems just to make sure we can handle them. So curve sketching, trig. All right, so the problem that we're going to be sketching is 2 cos x plus 2 sine x cos x. And we're only going to sketch the curve from 0 to 2 pi. So anytime you're doing a trig graph, you should look for that interval. I'd say 0 to 2 pi is pretty typical, but usually they're going to cut it off somewhere because these graphs go up and down forever, and that's a lot of maxes and mins and increasing and decreasing intervals to find. All right, so we're going to go ahead and find any x-intercepts or y-intercepts or asymptotes, anything like that, from the original function. So y-intercepts are the easiest to find. I'm going to go ahead and look for that first. So I'm going to say the y-coordinate when I plug in 0 is 2 times cos of 0 plus 2 times sine of 0 times cos of 0. Cos of 0 is 1. So we have got 2 times 1 plus 2 times sine of 0 is 0. And so that's just 2. So that means that we have a y-intercept of 0, 2. X-intercept is going to come when we set the original function equal to 0. So I'm going to say 2 cos x plus 2 sine x cos x equals 0. And for me to solve this equation, I could go ahead and factor it. So I can see that I have a GCF of 2, and I also have a GCF of cos. So I'm going to go ahead and take that stuff out. I have 2 times cos. And then for my leftovers, since I divided out the whole thing, that would leave a 1 behind. And then this would leave a sine behind. So I have 2 cos x equals 0. And I have sine x equals -1. So cos x equals 0 if I divide the 2 over. So I have to think about where on the unit circle do I have an x-coordinate of 0, and that's at pi halves and 3 pi halves. And I know that those are the only values that I need because I'm just looking at the values on the unit circle. That's the interval that we're using. And there's no number in front of x telling me that this graph has a different period than 2 pi. So I know those are the only answers I need. Then I look at the unit circle to see where I have a y-coordinate of -1, which would be at 3 pi halves. So that means that I have 3 x-intercepts. I've got pi halves, 0, and 3 pi halves. I don't have 3, I only have 2. One of them was redundant. So pi halves 0 and 3 pi halves 0. There's no asymptotes. This isn't a rational function. It's just trig. It doesn't have a tangent in it, so I don't see anything that would provide information to give me an asymptote, so I'm not worried about looking for that. And I think that's it for the original function. So now we're going to go ahead and work with the first derivative. So y prime, 2 times the derivative of cos would be -2 sine x plus, and then this is a product rule. So the first times the derivative of the second plus the second times the derivative of the first. So I have -2 sine x minus 2 sine squared x plus 2 cos squared x. And at this point, we have to think about taking a little trip back to pre-calculus, where we remember our trig identities. And I made you guys a sheet. Looks like this. So I'm looking at my sheet to see if I can take this. I need to be able to solve it, set it equal to 0 and solve, and that's going to be hard when I've got sines and cosines. So I want to be able to make this problem all in terms of sine, which means that I can take cos squared and replace it with 1 minus sine squared. And so I'm going to do that because then I can factor to solve for sine. So that leaves me with -2 sine x minus 2 sine squared x plus 2, and then this is where I replace with 1 minus sine squared x. And just make sure when you're writing notes on these that you're actually pausing the video and writing everything out. You shouldn't shorthand things. You want to show all of your work so that if you need to go back and look at what you did, it would make sense. All right, so I'm going to distribute that 2. And then I'm going to go ahead and combine my like terms and put everything in order. So I have negative 4 sine squared x minus 2 sine x plus 2 equals 0. And so now I'm ready to start solving. I'm going to go ahead and take out a GCF of negative 2. So that leaves me with 2 sine squared x plus sine x minus 1. And I need to factor this. So I'm looking for two things that multiply to negative 2, but add to positive 1. Multiply to negative 2, add to positive 1. So that'd be 2 and negative 1. So I keep the GCF in the front, but I've got sine x plus 2, sine x minus 1. The number that I slid over was a 2, so I'm going to divide each of those by 2. So I keep my GCF in the front. I have sine x plus 1, and I have 2 sine x minus 1. And so that means that now I'm ready to actually solve these factors. That gives me sine x equals negative 1 and sine x equals positive 1/2. And so I'm going to go ahead and look on the unit circle and see when I have these values. So the y coordinate equals negative 1 only in one place, and that's at 3 pi halves. The y coordinate equals positive 1/2 in two places, which would be pi over 6 and 5 pi over 6. And so now when I do my sign chart, I'm going to use those three values on my sign chart. So I've got 0 and 2 pi. I've got pi over 6, 5 pi over 6, 3 pi over 2. And so now I have to come up with numbers to plug in kind of in between those. So between 0 and pi 6, I'm going to say pi 7ths. That's kind of weird to plug in. Between pi 6 and 5 pi 6, I could plug in pi halves. I could plug in pi. I could plug in 7 pi 4ths. So it's not that I'm that good at fractions, it's that I was picturing the unit circle and I was like picturing what's in between those and that sort of thing. Okay, so if I plug these in here, I'm going to have a negative times sine of pi 7ths is going to be up, and plus 1, that's going to be positive. 2 times sine of pi 7ths minus 1. 2 times sine of pi 7ths is going to be a pretty small fraction. So I'm going to believe this is negative, but I might go ahead and check that on my calculator just to make sure that I didn't make a little error. So I'm going to say 2 times sine of pi divided by 7. Just going to make sure that I'm in radians. I'm not, I'm in degrees. Okay, so it actually was positive. Okay. Never mind, I was being silly. I didn't minus the 1. I was like, wait, that doesn't match my notes. It was 0.866, and then if you subtract 1 off of it, it makes it negative. Okay, so that means this whole thing is positive. If I try pi halves, I've got negative 2. Sine of pi halves is 1. 1 plus 1 is positive. 2 times 1 is 2. 2 minus 1 is positive, so it makes this a negative. At pi, we've got a negative times Sine of pi is 0, 0 plus 1 is positive. That's 0, 0 minus 1 is negative, and so that makes this a positive right here. And then 7 pi fourths, this is the one that's going to hurt my brain. Sine of 7 pi fourths would be negative root 2 over 2 plus 1. I believe that's positive. Sine negative square root 2 over 2. Yeah. 2 times sine of 7 pi fourths would be 2 times negative root 2 over 2, which is negative root 2 minus 1. That's definitely negative. Okay. Whew. That hurt my brain. All right, so we got that filled out. Now we can go ahead and write our increasing and decreasing intervals. So it's increasing from 0 to pi over 6. It's increasing from 5 pi over 6 to 3 pi over 2. It's increasing from 3 pi over 2 to 2 pi. It's decreasing from pi over 6 to 5 pi over 6. All right, so make sure when you write your increasing and decreasing intervals that if you have two intervals in a row that are the same, don't make them one parenthesis. They need to be two sets of parentheses, because at 3 pi halves, there's a horizontal asymptote right there. So that means it's not increasing, it's not decreasing, it's constant at 3 pi halves. So it levels out for a second, which needs to be reflected in your answers. Okay, so now let's go ahead and find the max, the relative max and the relative min. So we're looking at where it goes up and then comes down, where it goes down and then comes up. So the relative max is at pi over 6. The relative min is at 5 pi over 6. And to get the y-coordinates of that, we need to plug the x-coordinates into the original function. And so we're going to say f of pi over 6 equals 2 times cos of pi over 6 plus 2 times sine of pi over 6 times cos of pi over 6. So cos of pi over 6 is root 3 over 2 plus 2 times 1/2 times root 3 over 2. So 2 times 1/2, those are going to cancel. So I can see that I have a denominator of 2, so I'm not going to cancel out those 2's. I'm going to say this is 2 square roots of 3 over 2 plus a square root of 3 over 2. So we have 2 square roots of 3 and another square root of 3, which gives us 3 square roots of 3 over 2. Okay. I need to do the same thing with 5 pi over 6. So I'm going to have to use the back. All right. 2 times cos of 5 pi over 6 plus 2 times sine of 5 pi over 6 cos of 5 pi over 6. So that's 2 times negative root 3 over 2. Plus 2 times positive 1/2 times negative root 3 over 2. And so again, the 2 and the 1/2 cancel. And again, I can already see kind of what's happening here. So I have negative 2 square root 3 over 2 plus negative square root 3 over 2. And so altogether, that gives me negative 3 square roots of 3 over 2. Okay. Whew. Okay, so we've got that figured out. Let's go ahead and work with our second derivative. So I'm going to go ahead and write the first derivative at the top of the page so that I can use that. It looks like when I did my second derivative, I went back to the form of the equation that I had first, and so I thought about negative 2 sine x minus 2 sine squared x plus 2 cos squared x. This is my first derivative. It shouldn't matter which form of the derivative you use. If you want to use the version that was all in terms of sine, you could do that. I'm trying to think of what benefit. Sorry, not making a, well, okay. Maybe I'll show you guys what ended up happening if we did it this way. I'm trying to think like a student. So a student would probably not go back to a different form of the derivative. You probably would have just used the derivative that you had already simplified. So I'm going to go ahead and go back to that one. Sorry I made you write that down. I'm going off my notes. Okay. So that was the simplified form of our derivative that we used to solve. So now let's go ahead and do our second derivative. But before we do our second derivative, I'm going to rewrite this as sine x squared. The reason I'm going to rewrite it like that is because that's what it really means. And writing it like this is going to remind me I should be using the chain rule on it. So that's why I'm doing that. All right, second derivative. The derivative of the outside is negative 8. Keep the inside the same, times the derivative of the inside, which is just cos. And then the derivative of this piece would be minus 2 of cos, and then would be plus 0. Okay. So to find the points of inflection and all that stuff, we're going to have to take our second derivative and set it equal to 0. It's funny because this actually worked out easier than what I had on my notes. So I'll show you guys my notes right here. What I had done is I'd gone back and used the form of the derivative before we fixed it. So this is what we first got when we did the derivative. And I used that to get my second derivative, and it was kind of messy. I guess it just saved us one step. It just was a harder derivative to get, and then you had to combine your like terms. But then it actually works out to be exactly the same as what we did this time, but just with less steps. So that's kind of nice. So that should make you feel better in that when you are looking for the second derivative, it doesn't really matter which form of the derivative you use. You're always going to get the same answer, as long as you don't make any mistakes. Okay, so I'm going to go ahead and take out my GCF, which would be negative 2 cos x. And then write my leftovers, which would be positive 4 sine x plus 1. So negative 2 cos x equals 0, which means that cos x equals 0. And here sine x is going to equal negative 1/4, which means that I was avoiding using my calculator as much as I could, but this right here is not on the unit circle, so this definitely would have to be a calculator active problem. So that's kind of nice. If I look at the unit circle to solve for cos, the unit circle tells me that cos has an x value of 0 at pi halves and 3 pi halves. And then I'm going to go ahead and find the inverse of, sine inverse of negative 1/4. So we have x is approximately negative 0.253. That answer is not going to work for us. I'm going to go ahead and store this as x on my calculator. That answer is not going to work for us because it's not between 0 and 2 pi. So I'm going to take that answer and I'm going to go ahead and add 2 pi to it. So plus 2 pi. So x is 6.030. And then anytime we're looking at answers between 0 and 2 pi, we should always have 2 of them. The way that you find the second answer with sine is you do pi minus the original answer you got, which I stored as x. So pi minus x is 3.394. And I'll go ahead and on the side to my paper, I'm going to write down what the rules are for that. So for sine, you have pi minus the angle that you got first. That's how you find your second answer. And then for cos, the way to find your second answer is 2 pi minus what you found first. And for tangent, the way you find your second answer is you take the answer, you just add multiples of pi to it, and you can get more solutions. So in case you are not remembering that from pre-cal, that's how you can find some other decimal answers. Okay, so now we need to go ahead and make our number line. So pi halves, 3.34 would be close to pi, 394. 3 pi halves, and then 6.030 would be very close to 2 pi. Okay, and since this is clearly a calculator problem, I'm just going to go ahead and use my calculator to find values this time. So, but we can still write down some numbers that'll work to plug in. So I'm going to use like pi fourths. I'll go ahead and use pi, bigger than pi, like 5 pi fourths. And then 7 pi fourths is probably good. I might have to double check that decimal. Okay, so what I'm going to do is I'm going to store the number that I'm plugging in for x into my calculator. So I'm going to say pi fourths is stored as x. And then what I'm going to do is just plug it in to this derivative. I'm just going to plug it in this one. I have 8 sine x cos x minus 2 cos x. So that's definitely negative. Then I'm going to go ahead and take pi and store that as x. And then I'll plug this in again. It's positive. I'll take 5 pi fourths and store that as x. And then I'll plug it in again. That's negative. I'll take 7 pi fourths. 5.49, that works, okay. And store that as x, and then I'll plug it in again. It's positive. And then it was 6.030, I'm just going to use 6.1 and store that as x for the last one. I forgot to write a number in that interval. All right, and that's negative. I'm going to write real small 6.1. Okay. So now we're ready to write our concave up and concave down. And so concave up would be from pi halves to 3.394 and 3 pi halves to 6.030. And make sure that when you're writing your concave up and concave down that you're using the actual numbers where the second derivative equaled 0. Some of you guys I've seen using the in-between numbers that you like plugged in to find your signs, and that's not right. So just make sure that you're watching out. If it's confusing you to write the numbers there, then don't write them there, write them off to the side so that you don't accidentally get it wrong. So 0 to pi halves for concave down, 3.394 to 3 pi halves. And then 6.030 to 2 pi. All right. So for our points of inflection, we have 1, 2, 3, 4 of them. We've got pi halves, 3.394, 3 pi halves, 6.030. Okay. So, and we're plugging this into the original function, not to the derivative. So I'm going to do pi halves, stored as x, and then the original was 2 cos x plus 2 sine x cos x. And so that gives me 0. That's nice. I'm going to come back to that decimal in a second. 3 pi halves. Stored as x. Plug it in. 0. That's kind of nice. Okay. And then for these other ones, there's a pretty good chance we could use that decimal and be okay, but in calculus you should never use a rounded decimal to plug into something else. So that means that I need to go back and get the actual decimal. I should have stored it in my calculator, I just didn't think about it. So I'm going to add 2 pi to this. Okay, so I'm going to store that. I'll go ahead and store it as x. Okay, so now I can go back and plug it in right here. 1.452. Okay, and then I need the negative version. So to get the, or not the negative version, but the other version. So to get that, it was pi minus, no, not that one. It's pi minus the decimal that I just got. I guess that would have worked actually. 3.394 stored as x. Okay, and then I can go up here and plug it in. -1.452. Okay. So now I can go ahead and graph this little guy using all the information that I have. So I'm going to start off with my x-intercepts and my y-intercepts. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if we do this as pi and this is 2 pi, that'd be pi halves, 3 pi halves. Okay, so some of the information that we had on there was that we had a y-intercept of 0, 2, x-intercepts at pi halves and 3 pi halves. So I'm going to go ahead and count a few boxes. I just don't want this to be super tiny. So there's 0, 2, pi halves, 3 pi halves. We also have maximums and minimums, and we have points of inflection. So I already graphed this point of inflection, I already graphed that point of inflection, but I have 3.394, negative 1.452. Oh, it's going to be kind of hard to draw. I might hold off on that one for a second. Relative min and max, we can graph those though. So pi 6 and 5 pi 6, I just need to see what this decimal is. So that's 2.598. So I'm going to write 2.6 because I probably can't graph it more accurately than that. Okay, so pi 6, if 12 boxes is 1 pi, then pi 6 is going to be 2 boxes. Okay, so at pi 6 we have 2.6. So 2.33333. 2.6 would be a little bit underneath that. And then at 5 pi 6 we have the negative version. So 1 pi 6, 2 pi 6, 3 6, 4 6, 5 6, negative 2.33333, negative 2.6 would be like down here. Okay, so it says that it's increasing up until here, and then it decreases, 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 and then increases again. And we're checking our concavity as we're doing this. So it's going to be concave down from 0 to pi halves. So I'm going to say we're going to let it increase, but it's concave down. And then now it's decreasing, but it's concave down, so I'm going to make it look like that. Right? And then it's concave up, but still decreasing. Yep, until we get to 5 pi 6. And then it's going to be increasing from 5 pi 6 to 3 pi halves. And concave up is going to be just a little bit past pi. And then it's concave down again. So my point of inflection is not perfect, but somewhere in here I had a point of inflection where it changed a little bit. Just a little bit past pi. That point's not perfect. And then from 3 pi halves to 6, it's concave up. I'm going to need another point on here. Okay, so 6.030. 2 pi is 6.14, so it's going to be a little bit before that, and it's going to be 1.5. So 1.6, 1.5 is somewhere in there. So there's concave up. And then after that, it's concave down again, so then it's going to look like this. Ooh, kind of a strange looking graph there.